Fletcher. I was the reporter for Group 2, Section 2 for this practice lab. First, I'm going to start talking about the K thermocouple that we use. This is a diagram of a generic one that I found on the internet, but it gives you a good sense of kind of how the thermocouple works. So you have, for the K type, we have a chromal and an aluminal. Chromal is made of nickel and chromium, and aluminum has four different elements in it. They're welded at the tip where you see two cents right here, and the difference in temperature causes a voltage, which is read at the end over here at the meter, and that will give you the temperature. We recorded it on a computer for us. They do sell different handheld units, so it could be portable as well. All right, some of the equations that we used that we were given at the beginning for this lab. This is the first one. Now, we take that equation and we integrate it, and we get this equation right here, where it shows the temperature difference with an exponential with time raised to it. Now this, for the rest of the presentation, I call norm T. It shows up easier than saying normal T every time. And this is our 1 over time constant that we were looking for at the results, and you'll see that very shortly. Then through substitution and manipulation, we ended up finding T as a function of the logarithmic normal T, and then you still have tau over here as a negative. This first slide shows the ice bath temperature, and this was when we placed it in there. This is just temperature versus seconds. I highlighted 2 points right here. This is 24.15 I used as my starting temperature, and then the final ending temperature I got at 2.02 degrees Celsius. Now this is the warm-up after the ice bath. I highlighted a couple more points. I started at 2.03. You can see there was a very steep curve right here, and it ended at 8.08, and then the last temperature I used was 22.94 degrees Celsius. All right, now I used the normal T that we saw earlier. This is this red line right here is the equation of best fit for it. It's an exponential. Then this is the logarithmic of that. And this red line again is also the line of best fit for it, linearized. These numbers right here correspond to the equations that I showed earlier. This one right here is the 1 over tau from this equation. And then this, you can relate these two equations. This right here is the 1 over tau from this equation from earlier. When you use those values, which are the same, Excel did round a little bit differently. So you got an extra significant digit here than you do here, but you do get tau to be negative 1.859. All right. Now, when you take it out of the water, again, we have the norm T versus time graph with the exponential going down, and then this is the warm up. Now, for the warm up, I'm not sure if y'all can see this, but it does. The line of best fit isn't the greatest right here. It could be because of the data points that I decided to use, and I might have gone a little too far. But you can see that it started to drop off a lot right here, but it did fit fairly well at the beginning. All right, and then same exact scenario from last slide is this is the 1 over tau for each of the equations, and then the tau for this one came out to be a lot higher at negative 60.2. All right. Now, different time constants. Probably wondering why we have them. All right, it's because of the convective heat transfer. For the air and water, it's very different. So for air, it's a lot smaller than it is for water, and so because the air is H is on the bottom, as you have a smaller value there, it causes T to rise. All right. Now, I did the same for the boiling bath when we put it in the boiling water. These are just the slides of it being inserted into the water. And you can see the steep rise in temperature right here, and then this is pulled out. This is just temperature versus seconds. You don't get a whole lot of information, you just see the natural trend for it. Now what we wanted is, again, normal time right here. You get your exponential, and then the ln of normal versus time. You get your straight line right here. This one does seem to fit fairly well. It's not the greatest, but it's still is good for our purposes. Now we still have the 1 over tau from right here and right here. They match up. We're calling the past equations right here. You can see that's where you get the tau from. And finally, I got negative 1.04 for tau for this. All right, now out of water, same thing. And for tau for this one, you get negative 90.9. The results show that the ice bath and the boiling water, the towels, you can see cooling down in the air right here is a lot higher. Warming up in the air over here is a lot higher. Again, that goes back to the H values being different for the air and for the water. Now, also it changes because of temperature, your different materials that you use, and I believe it's very dependent on temperature properties of the materials that you use. All right, some errors and improvements. One, we use two different thermocouples, so using one of them would definitely help, and so you have the same readings for each. A thermometer. The only room temperature that we got was from the thermocouple. Instead of checking that with an actual room thermometer, we might have been able to use a different value at the starting temperature instead, or at least be able to double check it. All right, same thermocouple. We didn't get the expected readings that you think of. Boiling water, 100 degrees Celsius. Ice is 0 degrees Celsius. We were close, but we didn't get the actual theoretical values. And so we would be slightly off on our time constant if you're trying to do just strictly theoretical data. And then if we wanted, and I showed in my past slide that I may have used some data points that were not, that threw off the towel from the line of best fit. If we used like Chauvinot's criteria with standard deviation, we should be able to eliminate some of the extra noise in those data points, which would give us a better curve fit and a better and more accurate towel time. And that's it. Do you have any questions? Nope. And I did happen to throw in using a theoretical 0 and 100. This curve fit turned out to be a lot worse for some reason, so I didn't decide to include any of that, and then this was the variable definition.